CAN Bus Explained. A simple intro. In this tutorial, we explain the Controller Area Network, CAN Bus, in simple terms, including the basics, the key benefits of CAN, and a breakdown of the CAN frame. To get a practical understanding, we'll also explain how to record and decode CAN bus data. Let's start with the basics of CAN bus. To understand what CAN bus is, imagine that your car is like a human body. In this context, the CAN bus is the nervous system, enabling communication between different parts of the body. Communication happens between different CAN bus nodes, which are also called electronic control units, or ECUs. These CAN nodes are like parts of the body, interconnected via the CAN bus. Information from one node can be shared with other nodes. In an automotive CAN bus system, ECUs are things like the engine control unit, airbags, audio system, etc. A modern car may have up to 70 ECUs, and each of them may have information that needs to be shared with other parts of the network. This is where the CAN standard comes in handy. The CAN bus system enables each ECU to communicate with all other ECUs without complex, dedicated wiring. Specifically, an ECU can prepare information, for example, sensor data, and broadcast this via the CAN bus. The physical communication happens via the CAN bus wiring harness, consisting of two wires, CAN low and CAN high. The broadcasted data is accepted by all other ECUs on the CAN network, and each ECU can then check the data and decide whether to receive or ignore it. In more technical terms, the controller area network is described by a data link layer and physical layer. Specifically, ISO 11898-1 describes the data link layer, while ISO 11898-2 describes the physical layer. Today, CAN bus is standard in practically all automotives, like cars, trucks, buses, tractors, bikes, as well as ships, planes, EV batteries, machinery, and more. There are 4 key benefits to CAN bus that help explain the popularity. First, CAN bus is simple and low cost. ECUs communicate via a single CAN system instead of via direct complex analog signal lines, reducing errors, weight, wiring, and costs. Second, it is fully centralized. The CAN bus provides one point of entry to communicate with all network ECUs, enabling central diagnostics, data logging, and configuration. Third, CAN is extremely robust. In particular, the system is robust towards electric disturbances and electromagnetic interference, making it ideal for safety-critical applications. Finally, it is efficient. CAN frames are prioritized by ID, so the top priority data gets immediate bus access without causing interruption of other frames. To truly understand the CAN bus protocol, we find it useful to explain how to record and decode CAN bus data. CAN data acquisition is done across many use cases today. For example, CAN data from cars can be used to reduce fuel costs, improve driving, test prototype parts, and for insurance optimization. Similarly, CAN data from trucks, buses, tractors, etc. can be used in fleet management to reduce costs or improve safety. Another increasingly popular use case for CAN data is predictive maintenance. Vehicles and machinery can be monitored via IoT CAN loggers that communicate data to remote servers. This data can in turn be used to predict and avoid breakdowns. Finally, CAN loggers are increasingly being used as black boxes in vehicles and machinery, providing data for diagnostics and, for example, warranty dispute handling.